Hello class, today we're starting the chapter 12 information, which is energy, work, and transfer of energy. So first we're going to start with our comparison of potential and kinetic energy. So potential energy is just stored energy, and it's based on the position of the object or condition, usually the height. So energy has not been released yet. It's all stored in that particular object. Two examples: elastic potential energy would be stretching a rubber band or loading a spring, something like that. Gravitational potential energy, which is the one we'll spend time on, would be an apple hanging on a tree or a book on top of a shelf. So when we calculate potential energy, it will be, the equation is mass times gravity times height, with gravity being the gravity due to acceleration, which is 9.8 here on Earth. So our example problem: calculate the potential energy of a 20 kilogram object that is sitting on a shelf 5 meters above the ground. So potential energy would be 20 times 9.8 times 5. This is measured in joules, so our final answer, once you multiply that out, is 980 joules. Kinetic energy is moving energy, and this will depend on mass and speed. So a couple examples here. A small increase in speed produces a large increase in kinetic energy, and we'll show that in the equation here in just a minute. And the example that we had before was an apple hanging on a tree. Once the apple falls from the tree, it's doing work or releasing energy, and that would be kinetic energy. The equation is 0.5, or half, of the mass times velocity squared. Now, often I have students that mess up this equation. They either forget to do the half of the mass, the 0.5 times mass, or forget to square the velocity. So make sure that you're looking at that when you do this equation. In this example here, what is the kinetic energy of a 44 kilogram cheetah running at 31 meters per second? The kinetic energy would be equal to 0.5 times 44 times 31 squared. I suggest for a lot of you, when you put this in your calculator, that you do the 0.5 times 44, the 0.5 times mass first, get that number, do 31 squared, or the speed squared, second, and then multiply those two final numbers. Our kinetic energy here is 21,000 joules. So our transfer of energy is indicated in this picture here. We have potential energy at that height where it's stored energy and there's a height associated with it, so mass times gravity times height. Once that individual goes down the hill, that potential energy is transferring to kinetic energy, and the most kinetic energy they will have is going to be here at the bottom of the hill. Here we're putting energy in, it's moving energy, so it's kinetic energy, the most kinetic energy down here. It's decreasing kinetic energy as they go up and increasing potential energy until you reach this top point. At this top point, you're going to have the max potential energy and the least amount of kinetic energy. And then kinetic energy will be increasing and potential energy will be decreasing as they go down the hill till you hit max kinetic energy at the bottom of the hill. This is kind of showing that as well. Usually a roller coaster is a good example of that transfer of energy. Now, in the end, we have conservation of energy, which says that energy cannot be created or destroyed. So most of our energy is going to go from potential to kinetic. However, there are factors outside of the system that can affect it. So if we say we have 21,000 joules of potential energy, the kinetic energy will not equal 21,000. It's going to be less than that, depending on how much friction or sound or light or other things that cause some of that energy to transfer out of the system. The energy is not gone, it's just not usable. So, for example, in this example at the bottom, energy can be exchanged out of the system through friction, heat, which is thermal energy, or possibly sound. There's some other ways that it can transfer out, but just understanding that your kinetic energy is never going to quite equal your potential energy, even though we have this law that says that all energy is conserved. It's just that some of the energy is transferred out of the system into a kind of unusable form. Sometimes it is a form that you want used. Sometimes you do want heat out of that system. And so that some of that heat will be usable for the particular job that you're doing. If you're doing something with machines, you would want to have the most potential energy that you have stored. You want to use as much as you can. So you want to try and eliminate places where there's friction. You want to eliminate places where some of the energy could be transferred out of sound or light or things like that, and to get the most efficiency out of that machine. Okay, that's where we're going to end for today's notes, the introduction to energy.